Hi everyone, myself Konda Krishnudu, Assistant Professor of Physics, Department of Science and Humanities, MLR Institute of Technology, Hyderabad. In the previous class, we discussed about NDYAG laser. In continuation with that, today we are going to discuss about CO2 laser under the lesson lasers. So coming to today's overview of the presentation, first of all, I am going to explain about block diagram of a laser system. After that, particularly about CO2 laser. So under this, I am going to talk about its introduction, construction, working, applications, and finally conclusion. Now, as we know, block diagram of a laser system. Block diagram of any laser system consists of three parts: source of energy, active medium, resonating cavity. Source of energy is here. This is external energy source. The name itself implies that it is used to give energy to the particles of ground state so that they will move from ground state to excited state. The second part in the laser system is active medium. So active medium is here. So laser medium is nothing but active medium which is kept in a resonating cavity. So the actual laser transitions takes place in this active medium only. And the third part is resonating cavity. So we know laser works on the principle of lasing action, or it is nothing but repeated stimulated emission. So to get that, resonating cavity is required. Resonating cavity is nothing but a glass tube having two mirrors on either side of it. So this is about a block diagram of a laser system. Now coming to CO2 laser. CO2 laser. Coming to the characteristics of CO2 laser first. So CO2 laser is a molecular gas laser. So why it is called molecular laser? Because CO2 is a molecule with one carbon atom and two oxygen atoms on either side of it, and obviously it is gas, that is why it is called gas laser. So CO2 laser is a molecular gas laser and it is a 4-level laser. 4-level laser, and with the help of this it will emit continuous output. Coming to the active medium. So actually we are going to use carbon dioxide, nitrogen as well as helium in the discharge tube of this laser. That is called as active medium, and active centers are carbon dioxide molecules. Between the carbon dioxide molecules energy levels only we are going to get laser transition. That's why they are called active centers. And the pumping method in this laser system is electric discharge pumping. So generally in gas lasers we use this type of pumping, that is electric discharge pumping. And coming to the resonating cavity in this case, so discharge tube on either side of it is fitted with silicon mirrors, with one as 100% reflecting, the other for partially transparent. And coming to the output power from carbon dioxide laser is 10 kilowatts. So generally 10 kilowatts is considered as high power. So carbon dioxide lasers, they are available both in low power as well as high power. Nature of output, as we discussed, in the case of 4-level laser, generally the output will be continuous, and wavelength of output in this case is two types of outputs will come. One is 9.6 micrometers and the other is 10.6 micrometers. So based on the requirement we can take one as output and we can suppress the other. So generally carbon dioxide laser emits light in the infrared region. These wavelengths corresponds to infrared region of the electromagnetic spectrum, and lasing action is achieved by transitions between vibrational energy levels of carbon dioxide molecules. So regarding to this we are going to discuss in the next slide. So when we take fundamental modes of vibration of carbon dioxide molecule, it has three fundamental modes of vibration. One is called symmetric stretching mode, the second one is asymmetric stretching mode, and the third one is bending mode. Coming to the symmetric stretching mode. So we know carbon dioxide molecule is a combination of one carbon atom and two oxygen atoms on either side of it. In the first case, symmetric stretching mode, a carbon atom is fixed to a position and two oxygen atoms will vibrate on either side of it symmetrically, and hence the name is given symmetric stretching mode. And the second one is asymmetric stretching mode, where along with the oxygen atoms on either side of it, the carbon atom also vibrates, and hence it is called asymmetric stretching mode. And the third one is bending mode. So in this case, carbon atom remains fixed at particular position, whereas the oxygen atoms vibrates here up and down, and this is mode of vibration is called bending mode. So like that, carbon dioxide molecule undergoes 3 different types of vibrations. Now coming to the construction. So CO2 laser, generally it consists of a discharge tube of very large length when it's compared with its diameter. In this case, particularly the length of carbon dioxide laser, the discharge tube length is around 26 centimeters, and whose cross sectional area is 1.5 centimeter square. And this discharge tube is filled with 3 types of gases: carbon dioxide, nitrogen as well as helium. A mixture of carbon dioxide, nitrogen and helium in the ratio of 1:4:5 is used in the discharge tube. Now, so coming to the construction, so why we are using nitrogen and helium along with carbon dioxide? In the introduction for this CO2 laser, I told that the active centers are carbon dioxide molecules, means between the vibrational states of carbon dioxide molecule only we are going to get laser transitions. But what is the need of nitrogen and helium? If we question ourselves, nitrogen molecules generally they are light in weight when compared with carbon dioxide. That's why these nitrogen molecules are used to stimulate carbon dioxide molecules from their ground state to excited state. And coming to the next one, helium. So what is the purpose of helium in this case? So generally helium atoms are used to cool the apparatus. So they use it to relax the carbon dioxide molecules. As a result of that, they use it to cool the working apparatus during its operation. That is the need of nitrogen and helium along with carbon dioxide molecules. Now, we know any laser consists of 3 parts. So the first part is source of energy. In this case, we are going to give energy in the form of electric discharge. For that, this discharge tube is connected to power supply. So this is power supply, which is used to create discharge in the discharge tube. That is the first one. The second one is active medium. So this is active medium. Active medium is nothing but combination of carbon dioxide, nitrogen and helium in the ratio of 1:4:5. That is about the second standard part. And the third one is resonating cavity. Resonating cavity is nothing but the discharge tube having 2 mirrors on either side of it. One is fully reflective mirror and the other one is partially transparent mirror. Along with this mirror arrangement, in this case, we will have Brewster's windows. So Brewster's windows, maybe they are used as a single, sometimes they are used as a pair of Brewster's windows. So generally output we are going to get from the partially transparent side of the resonating cavity. In this case, the output, as we came to know that it is 10.6 micrometers, which falls in the infrared region, right? So generally laser light or laser beam which is coming out from laser device possesses laser properties like monochromaticity, coherence, intensity and all. Along with that, in this case, due to this Brewster's windows arrangement, this laser output is going to have a polarized output. Polarized output we are going to get because of the Brewster's window arrangement. Sometimes these Brewster's windows are also used to suppress the unrequired output radiations and or to get particularly required output like 10.6 micrometers. Now coming to the energy level diagram. Using this energy level diagram, we are going to discuss the working of CO2 laser, how CO2 laser works and how it is capable of producing output radiations. Now see here, these are the energy levels of nitrogen. This is ground state energy level of nitrogen and this is excited state of nitrogen molecule. So generally when we create discharge in the discharge tube, what happens? Electrons moves from cathode to anode. Electrons moves from cathode to anode. While they are moving, they will collide with nitrogen molecules. They will collide with nitrogen molecules so that nitrogen molecules enters into excited state. When we initiate discharge in the discharge tube, electrons moves from cathode to anode. On their way, they will collide with nitrogen molecules so that nitrogen molecules will sent into excited state from ground state. Now these excited nitrogen molecules, what they will do? There is a special process called resonance energy transfer. So through that process, the excited nitrogen molecules will supply energy, or they will stimulate ground state carbon dioxide molecules, so that they will move from ground state to the excited state E5 here. Now excited nitrogen molecule stimulates ground state carbon dioxide molecules, so that carbon dioxide molecules will enter into excited state. Here CO star represents excited carbon dioxide molecules. So these excited carbon dioxide molecules will be there in the energy level E5. So in this case, energy level E5 is considered as metastable state. Energy level E5 of carbon dioxide molecule is considered as metastable state. So in the previous classes we discussed what is metastable state and its role. We came to know that metastable state is the excited state having longer lifetime, and because of this metastable state only we will get laser transition. Metastable state plays a very important role to get population inversion. So in this case, E5 is considered as metastable state. Now we are going to get laser transitions between the energy level E5 and E4 as well as E5 and E3. So two laser transitions we are going to get in this case. One of the laser transition is due to transition of carbon dioxide molecules from E5 to E4. Another important transition here is E5 to E3. In both the cases we are going to get laser transitions. So all this information is placed here in this slide. Now coming to the E5 to E4 transition. E5 to E4 transition corresponds to 10.6 micrometers. Whereas the transition from E5 to E3 corresponds to 9.6 micrometers. So as we know, the role of Brewster's windows in the carbon dioxide laser is to suppress any one of the radiation. So generally 9.6 micrometers radiation will be suppressed using Brewster's window arrangement, and finally 10.6 micrometers output we are going to get from the laser device. So after getting laser transition, all the atoms from E4 and E3 will fall into E2 as we discussed, and after that they will fall into ground state, and after that they will fall into ground state. So carbon dioxide molecules at E4 and E3 fall into E2 by the process called inelastic collisions. So in this case the collisions are inelastic, and simply they will move from E4 and E3 to E2. After that CO2 molecules falls into ground state by non-radiative transitions. Non-radiative transition. The transition between E2 and E1 is non-radiative or radiation-less transition. In this case, what happens is energy releases in the form of heat, right? And again, nitrogen molecules will stimulate some more carbon dioxide molecules from ground state to excited state. So again, the process, this process will continue. That is how carbon dioxide laser is capable of emitting 10.6 micrometers output. Now, what are the applications of carbon dioxide laser? So carbon dioxide laser has so many applications in the field of science and technology. So it is available both in low power as well as high power. So high power lasers, high power carbon dioxide lasers, generally they will find applications in industries. So particularly they are used for cutting of plastics, wood and glass. High power carbon dioxide lasers are used for cutting of plastics, wood and glass. And not only plastic, wood and glass, they are also used for cutting, welding and coating of metals. Carbon dioxide molecules are also used for coating and cutting of metals such as stainless steel, aluminum or copper. And also carbon dioxide lasers find applications in laser marking of various materials. So laser marking purpose they are used. Engraving some letters on glass or some other metals. In that case also carbon dioxide lasers are used. That is called laser marking. And they are also used for laser hardening. They are laser hardening. Hardening is nothing but heating the substance for various purposes. And finally, ablative lasers such as carbon dioxide lasers are excellent choice for patients with mild to moderate facial scars. So in medical field, carbon dioxide laser, generally low power lasers are used in low power carbon dioxide lasers are used in medical field. So they are used to remove scars, wrinkles, and as well as pigmentation. Also, these ablative lasers they are used in medical field. Particularly, they are used for skin treatment. So that is how carbon dioxide lasers are available both in low powers as well as high powers. Both will find applications in various fields. Low power CO2 lasers find applications in medical field, whereas high power carbon dioxide lasers find applications in the field of industry for various purposes. Coming to the conclusion, today we discussed about the block diagram of a laser system, how any laser system will work, and also we discussed particularly about carbon dioxide laser. Carbon dioxide laser, its introduction, working, as well as construction, and finally the applications of carbon dioxide laser. And continuation to this, in the next class we are going to discuss about one more important laser which is in the syllabus or which is in the lesson, that is ruby laser. Thank you.